So again, just kind of like that extreme value theorem, we check to see if the function is continuous on the closed. Now we're checking to see also is it differentiable on the open. Now we're going to look to see if f of a equals f of b. All right, a and b being the endpoints of the interval. So we're going to plug it in, plug both endpoints into the function, and then see if they're equal. If they're equal, then you know that there is at least one number inside the open interval, and that's important, one number in the open interval, such that the derivative at that number equals 0. All right, so what does that mean right there? It means if the derivative at that number equals 0, then that means the tangent line has to be horizontal, right? Because the derivative is 0. That means the slope of the tangent line, so the slope of the tangent line at that point C is going to be a horizontal line. Okay, so in other words, what? A peak or a valley. All right, the function is going to be curvy like a polynomial curve. It's going to have some peaks and valleys, so those peaks and valleys are going to occur somewhere in there. Okay, all right, now let's take a look at it from a graphical standpoint. All right, graphical representation. All right, so let's suppose we're just going to look at this in our first quadrant. All right, we're going to go with a relatively simple, straightforward parabola here. All right, because if that's my f function, if that's f of x, all right, let's say I want to examine, obviously we know it's what? Continuous, because it's a parabola. We know that it's differentiable everywhere because there's no holes, there's no jumps. There's no vertical asymptotes. It's a polynomial curve, so it's differentiable everywhere. So it fits. All right, those first two things. All right, now let's say I'm going to look at a given interval on this curve. Okay, let's say that maybe A is right here, and then let's say maybe B is right here. All right, we want it to be a closed interval, so let's go ahead and make these square brackets, I guess. I'm looking at it. It's closed. All right. So f of a will come up until we hit the curve. We'll say it's right there. On b, we'll come up. Ooh, I didn't do a very good job here of drawing my picture. Let's move b over a little bit because I didn't do a very good job drawing my picture. I'm trying to set it up definitely so it works. So let's make sure our b is over here a little bit. All right, because why? That means now here is going to be the answer. F of a equals some y value. I don't know what it is. F of b equals some y value. So then that guarantees that f of a is equal to f of b, which was the second part. All right, now that means that inside this interval, somewhere I'm going to have a c where the derivative equals 0. All right, and I do. If I start drawing my tangent lines, all right, right in here, let's do it with a different color, right in here, that tangent line would be a horizontal tangent line. Okay, so this is my tangent line. And that means at this value right here of c, f prime of c equals 0 because I've got a horizontal tangent. All right, now the other thing which we're going to do through these 2 points here, f of a and f of b, what's that line called? If this is a tangent line, this is the secant line. And look at those 2 lines. The secant line and the tangent line happen to be parallel to each other, and they're horizontal. So they're parallel and horizontal. Okay, but the thing is, the theorem says there's at least one point in there that will occur. Now, could there be more than one point? Yeah, what if there were lots of hills and valleys going on in here? Then I'm going to have more scenarios where the secant line is going to be tangent to that, parallel to that tangent line. Okay, so let's draw another picture real quick. I'll give myself a little bit more room on this one. let's say here's my A. I'm going to make it work perfectly this time. And then let's say my B. Okay. Now let's say again, I'm using a polynomial curve. Okay, kind of bad for a polynomial curve, but we'll say there's my f of x. We need to verify, is it continuous? Well, yes, you just saw me draw it. I didn't lift my pencil. It's continuous. It's a polynomial curve. All right. Is it differentiable everywhere in the open interval? Well, it is because it's a polynomial curve, so no holes, no jumps. So it fits that. All right. F of A equaling f of B. Okay, well, I tried to draw it so that there's the secant line going through. So, yes, f of A equals f of B. All right, which was another condition. So there's the three conditions for the theorem. Okay, and then it says at least one value C. All right, but there is C1 because there is a horizontal tangent, so the derivative is 0. All right, here's another one where the tangent line is 0. The slope of that tangent line is 0. So there's another C value, C sub 2. All right, here's another peak or valley in there. That slope of that secant line is 0. So then there's a C sub 3. So there's 3 values of C inside there. All right, so graphically, visually, that's what's going on. The tangent line and the secant line are always going to, in Rolle's theorem, the tangent line and the secant line are going to be parallel, and they're going to be horizontal because every time we're saying that derivative equals 0. All right, now, the way I drew both of these, my f of A and f of B was away from the x-axis. Okay, so here's where f, I had them up above. I had them away from that. All right, but if the f of A and f of B was on the x-axis, wouldn't A and B be the x-intercepts or the solutions to the polynomial curve? All right, so it can be such that this secant line happens to land on the x-axis, in which case your A and B would be your x-intercepts. Okay, in which case we can find x-intercepts. There's the solutions to the equation. As long as it's a nice little polynomial curve that we could factor, then we could find those. So I wouldn't have to even give you the interval if I make sure that f of A and f of B are equal at 0. Okay. All right, so because your textbook's going to kind of go that direction in some of the questions. All right, so that's kind of the background. All right, so let's take a look at some of these. Okay. All right, now you really do have 2 parts in the directions. All right, you got to verify Rolle's theorem applies. So there's your part 1. All right, your part 2 is then find all values of C. So it's a 2-part question. You have 2 things you have to do. The verify part is what I am shortening from our online notes. Okay, so first of all, label and tell the person that's grading your paper what you're doing. All right, now I'm going to verify. All right, well, what do I have to verify? I've got 3 main parts. I have to know whether it's continuous on the closed. I have to know whether it's differentiable on the open, going off what the theorem said, and then I have to know whether f of A equals f of B. All right, so polynomial curve, right? So we know it's continuous. So you're going to say f of x is continuous, and it's continuous where? On the closed. And yes, that makes a big difference. All right. If it is continuous on that closed, all right, then we know it's differentiable as well. So yes, I'm checking, but I'm thinking it through. I know it is. So f of x is differentiable on the open interval from 0 to 5. All right, now all I got to do is I got to calculate f of 0 and I calculate f of 5. So f of 0, all right, can I do the math really quick in my head? 0 squared minus 5 times 0 is just going to be 0. All right, f of 5. Again, you might have to do a little bit of work there, but probably not. 5 squared is 25 minus 5 times 5. So that one also equals 0. Okay, so this one, it really is the x-axis, right? It's going to be at the x-axis. All right, so then I can just say, therefore, Rolle's theorem applies. That's the part that is shortened from the online notes. Okay, go through the 3 parts. Check to see if it's continuous. If it is, write it down. Check to see if it's differentiable, write it down. And you do have to include these intervals, closed and open, okay? Give the 2 values for f of a and f of b, and then just say it there. It verifies. All right, now, second part, find c. Okay, now, the find c part, all right, seems to be the hardest of what people try to do here, okay? But when I put this in the directions, that tells you how to find c. That says take the derivative and set it equal to 0 and solve it. That's what that's telling you to do. All right, so first thing I'm going to do is I'm going to calculate f prime of x. So calculate your derivative. All right, so 2x minus 5. Okay, and then do what the directions tell you to do. Set the derivative equal to 0 and then solve it. So then I'm going to go 2x minus 5 equals 0. Solve that. Add 5 to both sides. So 2x equals 5. X equals 5 halves. Okay, now you're going to check, is 5 halves inside this interval? 2.5, right? So it's inside that interval. If 5 halves is not inside that interval, then it's not a value c that's inside that interval. Okay, it's got to be inside the open interval. Stop and think about what that theorem said. Okay, let's go back and look at it. If f of a equals f of b, then there is at least one number c in the open interval such that that is that. All right, so if this value right here would have been 5, would the theorem work? No. Okay, so you do have to pay attention to that. All right, once you get there, all right, then I know I worked this out in terms of x because this was in terms of x. Technically, I'm finding values of c. All right, so I could have worked this whole entire problem out with c, but I didn't because I wrote the function in terms of x. So in your therefore statement, let's have an overall therefore statement. Therefore, f, no, here, let's not do that. I'm going to kind of wing this one. Therefore, since c equals 5 halves is, since that value of c is in the open interval from 0 to 5, and the derivative at 5 halves equals 0, well, I don't like this one, then c is guaranteed to be 5 halves. I probably could have wrote a better one there. Yeah, that's close enough. Since c equals 5 halves is in the open interval, and the derivative at 5 halves equals 0, then I'm guaranteed to have c equaling 5 halves.